All right, we're going to go ahead and get started with session A. Our first speaker is Professor Nicolas Papernot. Nicolas is an assistant professor of computer engineering and computer science at the University of Toronto. He also holds a Canada CFAR AI chair at the Vector Institute and is a faculty affiliate of the Schwarz-Riesman Institute. His research interests span the security and privacy of machine learning.
Thank you, Sierra. I'm very excited to be here today. Thanks for waking up on a Monday morning to hear about machine unlearning. So today I'll do two things. First, I'll give you a sense of what kinds of mechanisms we can use to try and delete training data from machine learning models that have been deployed. And then I'll talk a little bit about how we can go about evaluating how well these mechanisms have deleted these training points. Before I get started, this work is, of course, work that has been led by many of my students. So thank you again, Sierra, for inviting me. I hope people here will ask you about your wonderful work on synthetic data and how it impacts generative machine learning. This work here on machine learning, as the slide indicates, is largely led by Envith, who is currently listening to me from the live stream just outside this room at the volunteer desk. So if you want to ask questions, you can blame me for all the mistakes and congratulate him for the good results. So what do we mean by unlearning? Well, there's really multiple motivations. When we started this work, we were inspired by privacy legislation. So in particular in the European Union, they've sort of pioneered this right to be forgotten, right? Where people had initially given their data to a company, and then the company trains a machine learning model on this data. And now we're asked, what do we do once these users retract access to their data? But recently, there's been a lot of interest in unlearning for other reasons. The first one listed on the slide is poisoning, in the sense that if we have data that we realize has been manipulated by adversaries to force us to learn corrupted patterns, we might want to be able to delete the effect of that data without having to retrain the model from scratch. And then the second one that has been discussed a lot, in particular in the press, because of all the lawsuits that are being pursued at the moment, is dealing with copyright claims, right? So if you have a model in particular, now that we have a lot of interest in generative machine learning, these models are outputting data, and so this brings up a lot of copyright concerns. And so machine learning could be one way to deal with it. But for the purpose of this short talk, I will focus on the third motivation. So really, this is an individual, one of us in the room, that is interested in deleting their training data in the interest of privacy. So when we started doing this, doing research on this topic, this was back in 2019, we looked at first sort of the naive solution to unlearning, which is essentially to retrain the model from scratch. Okay, so this is of course very expensive. So the first thing we asked ourselves is, can we actually modify the training algorithm proactively to make it easier to retrain the model once we get an unlearning request? And so what we did in this work is we first realized that rather than training one large model, it's easier to unlearn if you've trained an ensemble of different models on disjoint partitions of the training data. So here what you see on the right hand, so I'm tall but not tall enough to point up there, so I'll use my cursor, is that if you have one particular point that is in one of the partitions, now you only need to retrain the corresponding model rather than retrain all the models in the ensemble, and that is going to be cheaper than retraining one model trained on the entire set. So that's one easy modification we can make. And what it does is it essentially trades off accuracy for the speed of unlearning, because of course, the more of these partitions we have, the less data each of these models has to learn. And so they're going to be having a lower accuracy eventually. The second observation we made is that we actually can modify the order in which the training points are being analyzed. So typically we were looking at neural networks here. We use stochastic gradient descent to train neural networks. And in particular, we use the mini batch variant of that, which means we go through essentially in most implementations, we go through epochs where we essentially go through the entire data set at each epoch, okay, which is an approximation of all this. And so the problem with that is that from the first epoch, we've already analyzed all the training points. And so instead, what we notice is that we can gradually introduce the training data during the training algorithm so that we have intermediate checkpoints that have not been contaminated by all of the training points. And so very concretely, what happens is, for instance, you can start by training on 10% of the data. And then before you introduce an additional 10% of the data, you save the model parameters. And then you introduce the additional data. Again, you save the model parameters and so on. And so here what you're doing is you're essentially trading off storage space for unlearning cost. And if you have sort of unlimited storage, you can expect to have significant decreases in the unlearning cost, because you're essentially decreasing the expected number of steps that you have to repeat given any unlearning request. So this was a bit of progress, but it's still fairly expensive, because what we've done is we've made retraining from scratch easier by saving useful intermediate information, but we haven't sort of circumvented the need to retrain the model. And so essentially since 2019, sadly, we haven't made much more progress in coming up with an unlearning algorithm that has strong guarantees for the end user. And I'll explain what I mean by this in a few slides. But there is one line of hope, which is that people have largely shifted in terms of the machine learning paradigm that they're deploying. In particular, a lot of the models that we use today in our research are essentially following this two-step process where we first pre-train a machine learning model and then we adapt it to a downstream task. So if we forget about the pre-training, the pre-training was here. So if we forget about the pre-training for a second and we focus on the task adaptation phase, then what we observed recently is there is a lot of potential for unlearning mechanisms that are a lot more tractable than retraining from scratch. So there are specifically two paradigms that people are exploring. The first one is fine-tuning, which is simply an extension of pre-training, but now running the training algorithm on the downstream task data set. And for this fine-tuning approach, of course, we can use the same approach that I just discussed, this one, to unlearn. And why will this be more tractable? Well, essentially, you're fine-tuning for a much smaller number of steps. But what's interesting is this prompting paradigm, which is in particular pervasive in language models, because here what we're doing, instead of continuing to train the model, we're simply selecting a handful number of examples from the downstream task data set and including those at inference as we're asking the model to predict. And so here there is this question: can we hope to do better than sort of the CISA approach that I just talked about? And so here, to understand what's going on, we have to look a little bit at how these examples are selected. So sort of the naive thing that you would do is you would take your task adaptation set and you would select a random subset of these examples. Of course, the downside of that is that it's not going to give you very strong accuracy when you ask the model to predict. So what people have done is sort of the second row in the table here is that they've done some form of clustering analysis, in particular k-means analysis, to select examples that are close to the centroids and include those in the prompt. And so here the upside is, of course, the higher accuracy of the model once it's prompted. The downside is that now if you want to unlearn this sort of task adaptation, you have to repeat the k-means analysis if you remove one of the examples in the task adaptation dataset. But what we observed in the preprint that's right here is that you can actually use a variant of k-means that is quantized to essentially get stability with respect to the removal of individual task adaptation examples. Okay, and so what this gives you is that now the centroids that your k-means is going to return are going to be stable if you remove one of the examples in the task adaptation dataset, right? And so essentially, the degree to which you quantize allows you to control sort of a trade-off between the unlearning cost and the accuracy of the prompted model. And so if we look at experimental results, and I won't go into the details here, I'll just give you the high-level takeaway. What we can see here is we look at the performance on the vertical axis of different approaches to unlearning. On the left, we have this new approach here based on quantized k-means, and here we have the fine-tuning based approach based on CISA, the first approach that I discussed. What you can see is that as you vary the hyperparameter of these approaches, you get sort of different trade-offs between the model accuracy and the cost of the unlearning operation itself. But what's more interesting to me in these results, and these are just one example, there's a lot more in the paper, is that it shows how important it is to capture the cost of inference once you deploy the unlearned model. And in particular, here in the approach based on prompting, we're now varying the number of examples that are contained at inference to make a prediction. And so this has a direct consequence in terms of the cost to make a single prediction, okay? And so what we observed is that a lot of work that has been done in this field doesn't capture essentially the number of inference requests that we expect to respond to after we've processed a single unlearning request. And this is important because you can essentially move the cost of unlearning altogether to the inference phase. And on paper, if you only look at the cost of the unlearning operation itself, it looks like it's now extremely cheap, computationally speaking. But actually what you've done is you've just pushed the cost to inference, which is not sustainable if you want to deploy the unlearned model. So this is really important as people are evaluating these new approaches. But to conclude, I'd like to ask the question, how do we convince the user that we've actually unlearned their data, right? And this is a question that we still don't have a very good answer to. So that's why I have the spoiler alert at the bottom of the slide, which I added after giving this talk many times and people always asking me, what's the solution? So I don't have the solution. But what I can tell you is we have a definition problem. So here, what I've assumed so far is that we train initially from this data set, we obtain a model. And what we want to do by unlearning is obtain this model M prime that is equal, I'm going to clarify what I mean by this, to a model M double prime that we could have obtained by training on the model on the data set without the data to be unlearned, okay? And so there are two things that we need to figure out. First of all, what is this magic process, the unlearning mechanism, and what it means for models to be equal, okay? And so when we retrain from scratch, when this red arrow is retraining from scratch, it's pretty clear why we get the same distribution of models for M prime and M double prime. But as soon as we try to approximate retraining from scratch or come up with algorithms that are different from arrays that I just talked about in prompting, then we have to start evaluating the distance essentially between M prime and M double prime. And how you capture this distance is still an open problem. You could do it at the level of the predictions that these models make, but then that distance will be very sensitive to the points that you evaluate this distance on. Or you could do it at the level of the weights, but then we know that some models have, for instance, different weights, but identical predictions, right? So neither of these are very satisfying. I don't think I have time, 1 minute, so I will not explain why differential privacy is not a very good fit for this, but I will tell you how we're learning from differential privacy research to essentially inform how we compare models in the context of unlearning requests. And in particular, what happens is differential privacy is a notion of privacy that is agnostic to the data set that is being processed by the training algorithm. So it's a privacy guarantee that holds no matter what data set the training algorithm is going to operate on. And essentially, the high-level takeaway is that if the model is strongly differentially private, then adding or removing a point is not going to change if the training algorithm is strongly differentially private, adding or removing a point is not going to change the model that the training algorithm returns. And so you could imagine that if you have a differentially private training algorithm, you don't need to unlearn. And so what we've done in recent research is essentially come up with a variant of differential privacy analysis that is dependent on the data set that the training algorithm is processing, so that we can avoid the very high cost in terms of accuracy that comes with training with differential privacy, but still get that rigorous perspective on how individual training examples contribute to the model that we eventually obtain from running the training algorithm. Okay, and so this has given us a couple of results here, the first two papers, where we showed that we can leverage data-dependent analysis from differential privacy to reason about whether or not we need to unlearn a particular data point. So that's essentially where I want to leave things. A couple of takeaway messages. The first one is, as I showed in the work on prompting, we really need to capture the cost of deploying these unlearned models in addition to capturing the cost of unlearning itself. The second one, and what I just talked about with respect to differential privacy, what our research shows is that unlearning needs to be an algorithmic guarantee. You cannot decide whether a model has unlearned or not simply by inspecting the model itself. And the high-level intuition for this is that if you have a model on a loss surface, there are multiple gradient descent trajectories that lead to that same model. So if the user, you're inspecting the model, you have no way to know which trajectory was taken to arrive at that model. So you don't know if it was unlearned or not. And to better approach verifiable unlearning, I think we essentially need to understand how different training algorithms prioritize some of these gradient descent trajectories over others. So this is the end of my talk. Thanks for your patience with me going over time. And I would like to also thank our sponsors as well as all the students that have contributed to these projects. So thank you for your attention. I'm happy to take questions.